get to the last type of special transformations. Our first special transformation we did in chapter 2, where you could square root any graph. That one, you found out where the y values were 0, where the y values were 1. Between 0 and 1, it was slightly above. After 1, it was below. Next, and we did this just the other day, a couple days ago, we did 1 over any graph. And that's where you had non-permissible values. It's very similar also to chapter 2. Could have probably done it in chapter 2 as well, where you have non-permissible values becoming vertical asymptotes. A 1 over f of x graph never has x-intercepts because it is 1 on the top. And lots of asymptotes, and all that happens to the y value is you make the y value 1 over y. Because here's where the old y, f of x is like the old y value, and now you have 1 over the y value. And the last thing we look at today is y equals the absolute value of f of x, which all that's going to do is change all your y values to positive y values. So it's going to take the graph and flip it up over the x-axis. So in this graph, does it make sense that the entire graph will be above the x-axis? Some of these we could do using transformations. So again, if I wanted to graph the absolute value of 2x plus 3, I could take my absolute value graph and have a horizontal compression and a horizontal translation and do it that way. I'll review that after we learn the new technique. But just like the techniques for the square root graph and the 1 over f of x graph, we are going to graph the inside first. And we'll do that over here separately. So 2x plus 3, really easy to graph. It has a y-intercept of 3, a slope of 2, down 2 over 1, down 2 over 1. And we're going to want to label not only the y-intercept, but the x-intercept is going to be a very important point for absolute value graphs. So in this question, if you plugged in 0 for y and solve for x, I hope that you can see it's at negative 3 over 2, comma 0. Now to graph the absolute value graph, if the only thing that happens is that your y values change to, right? Your y values are going to change to the absolute value of y. That's going to flip the negative y values over the x-axis. So my positive y values, like 0, 3, it's going to stay the same. In fact, even the x-intercept at negative 3, 1/2, this whole section here stays identical because the y values were already positive. So putting the extra absolute values is not going to change them. However, the other part, and for example, you could plug in a point. For example, if I plug in negative 3 in for x, I'm going to get negative 3, negative 3. But on my graph, it's going to flip that over the x-axis, and it's going to become negative 3, positive 3. Can you see how this section here is getting flipped up to become that section there? And that is the only rule for absolute value graphs. Graph your original function first, then you're going to take wherever the y values are negative, they're going to get flipped up over the x-axis and become positive. Now, had you graphed this, right? There's my parent graph. In transformations, if I wanted to graph 2x plus 3, I'd have to first write it in factored form. That's the first thing you guys always forget. And then this would be a horizontal compression. You'd multiply your x values by a half. And this would be a horizontal translation, 3 over 2 to the left. So a little review of transformations here. Can you see this graph has been compressed? It's a little bit narrower than your regular absolute value graph. And then the 3 over 2 to the left is obvious. However, I would argue, I think the new method is actually easier. Easier to graph the inside and just flip up the part that was below. Especially when you have more than one transformation. And what's also really nice about the new method is that you can do graphs that you haven't seen before. So here's f of x, and I'll give you time to graph it out here. It's a polynomial function in factored form, so you would know that there were x-intercepts at negative 3, 0, 0, 0, and 2, 0. And because it would have been, if you multiply it out, right, this is an x cubed graph, which is odd. It's a positive x cubed graph, so its end behavior looks like this. Each x-intercept has a multiplicity of 1, so it goes straight through, starting down here, straight through. You don't know how high or how low it goes, but this would be enough. Okay? So a little review of chapter 1 graphing. Now that I have that graph, can I graph the absolute value of this function? Yes. The absolute value of this function, first of all, wherever the graph was positive to begin with, maybe you change colors on yours, that part stays the same. Because if you absolute value a positive number, it's going to be the same as it was. But everywhere where it was negative, it's going to get flipped over the x-axis. So this would be the graph of the absolute value of f of x. I took my original graph, and any places where the y values were negative, I flipped them up over the x-axis. We're going to do one more example, and that will officially end. So I'll call this example 3. Given f of x equals x squared minus 4. We're going to graph y equals the absolute value of f of x minus 4. So first of all, we've got an f of x graph. I'll graph that first. I know it has a vertex. It's been parabola translated down 4 units. I know that its x-intercept would be at 2, 0, and at negative 2, 0. So there's our original graph. This, and I'll label it, this is the f of x graph, or y equals x squared minus 4. Now what's interesting in this graph is we have the absolute value, but then you see that there's a -4 afterwards as well. Okay? So in this graph, we're going to do the absolute value, and whatever graph we get, what does a -4 afterwards do? It's another translation 4 units down. So I'm going to do this in 2 steps. I'm first going to graph in green here just the absolute value of f of x, just that part. What is that going to do? It's going to keep 2, 0 and -2, 0, and it's going to keep everything on this side exactly the same. But it's going to take this part that's below and flip it up. So 0, -4 is going to become 0, 4, and that bottom section would get flipped up. And it's not hard, but if you've never seen it before, you might feel like, well, how do I deal with this extra -4 afterwards? Well, that extra -4 is a translation down, right? It's back to transformations. It says, whatever this graph is, which is your green one, take it and move it down 4 units. So I'll draw a third graph. And in this third graph, everything gets moved down 4. I'm going to do this in purple. So I'm going to have 0, 0, because that's 0, 4 moved down 4. I'm going to have 2, -4, and -2, -4, because that's those x-intercepts moved down 4 units. And my shape looks exactly the same as the green shape, just moved down 4 units. And this, the purple one, is the graph of f of x